This random measure we've seen a way of constructing this random measure with a can approach, right? Okay, we have for instance, and you can construct it with H1 expansion, or we've seen the white noise decomposition too. Okay, but you can also construct this measure. Say you may want to make a convolution of your field with some modifying function. Okay, and this gives you a field x epsilon. Okay, this is a natural way of constructing an approximation of a bad function. Okay, you make a convolution with something smooth. Okay, so the question is, so define m bar like this. Okay. So obviously you may ask the first question. Okay. Does m bar epsilon converge towards some measure m bar? Okay, and in which sense? So, say in law, or second question, in which sense? If yes, in which sense? So, for instance, probability or law. Okay, and if you've got a yes to each of the two first questions here, the last question you may ask is the limiting measure m bar the same as that we constructed already? Okay. So question 3: are these measures the same? And the same in which sense? In law, almost surely, okay, depending on the convergence you get. Okay, and what I'm going to explain today is that you can answer a yes to each question here. Okay, and actually, what I want to show you is that provided that you know how to construct this measure, okay, you can answer yes to each question here. Okay, so I want to explain how to have a yes to each question with the GFF, but in the lecture notes you will find a more general statement. Here I just want you to have a picture of how it works. So so the first theorem about convergence and uniqueness in law. So I'm going to state a theorem which is the building block to treat all these questions. And this is an improvement of some paper by Robert, Vargas and myself. So basically, it means that as soon as you take a cutoff, okay, as soon as you take a cutoff, call it x epsilon. If you have some reasonable estimates on this cutoff, you will get a limiting measure for this measure in law, and the law does not depend on the cutoff you choose. Okay, so how to state it? Take well, let's take G a domain of Rd. Well, we have a GFF, so let's take a domain of R2. And call G delta so the distance, this is the set of points which are distance delta of the boundary. Okay, so you have a domain G, and just take G delta inside. You are at distance delta from the boundary. Okay, you have delta here. So take your kernel K as the green function of the Laplacian with directly boundary condition. With directly condition. And recall that recall that you have the following decomposition of the green function. Inside, when you are in the interior of G, the green function takes on this form, okay, with a continuous function and bounded on G delta. Okay, this is why I use this G delta thing, because you know that for the GFF, the function here may blow up along the boundary. So I want to be far away from the boundary, okay? Well, now I'm going to give you a criterion characterizing the nice cutoff of your Gaussian free field. So say we call them K Gaussian approximations. Well, a sequence of Gaussian centered processes call it X epsilon is a K Gaussian approximation if, well, first each of your field is defined as a measurable function. Well, it is random. It's Gaussian, so it is random. And if it approximates this kernel here in a good sense. So we define a constant CA, which is the limit sup as epsilon goes to 0. So in a way, we want to evaluate what happens outside of the diagonal of this kernel. So the criterion is the following: sup So I end my line here, minus g of xy so if this quantity here, sorry, the expectation ends here, well, well, if the quantity Ca is bounded on 0 plus infinity and Ca goes to 0 as A goes to infinity. Okay? So in a way it means that your cutoff, well, must be at short scale like log of over 1 plus 1 over the distance plus epsilon. It means that you have regularized your log at scale epsilon. Okay? And outside of this diagonal term, I mean when x is far away from y, it goes to 0. Okay, the difference have to go to 0 when x and y are far away from each other. But when you are very close, when x is close to y, you must be like a log, regularized at scale epsilon. Okay. So if you have a if you have this kind of cutoff, so the theorem is the following: if you take this was not this was just the beginning of the setup. Here is my definition, and now is the theorem. Take 2 K Gaussian approximation well, let's call them x epsilon and x bar epsilon. Then the couples well, then the couples converge in law. Well, I mean, what I want to say that this one converges in law if and only if this one converges in law, converge simultaneously or not. Well, I'm not sure that my sentence is clear, but what I mean is that if this couple converge, this one too, and conversely, and if this couple diverge, this one too. Okay, and if they do, the limiting distribution are the same. Well, okay, so basically the thing is that you have to show that for a cutoff of your choice, your favorite cutoff, you have to show that this couple converges, and if you manage to do so, you will know that for every reasonable cutoff, I mean reasonable means this condition here, you will be sure that this couple will converge. Okay. So basically, in the following, my favorite cutoff will be that of Kahn, and I will play with this statement to show the convergence of convolutions. Okay. So Well, a word about this criterion. Well, it has been, well, I don't know precisely to which extent it is true for every cutoff, but what I'm sure is that I've never met a cutoff which does not satisfy this criterion. So I cannot tell you the boundary of this criterion, but every cutoff I meet is okay. Okay, so all my examples are okay. Okay, so for the GFF, you can take the convolution, this works. Well, this is especially well fitted for the convolution cutoff. You can take the circle average of your GFF if you want. They will satisfy this condition. Well, for instance, the white noise decomposition of the GFF I gave you satisfies this criterion. Okay, so if you have if one day you find an interesting example which does not satisfy this criterion, send me an email. I'll be happy to see something out of this class. Okay. Well, I'm going to. Well, I will admit this theorem, but let's say that in the lecture notes you will see that this is based on Kahn comparison principle, rather on the proof, because he has an explicit method for evaluating the functional of these two things. Okay, and you can evaluate the difference of these two objects with integrals. And when you look at your integrals, if you want to see that the difference goes to 0 as epsilon goes to 0, you see that this criterion is what you need to see that the difference goes to 0. Okay? So the details are in the lecture notes, but it's a bit technical, so I don't want to, and I have no time to show you the proof. Well, this is just about evaluating integrals. So I rather want to explain you how you can. So this is just a statement about this convergence in law, because here I mean the limiting distribution, I mean law. Okay. So the question, you have some kind of answer to the question 1 about when we are talking about convergence in law. Okay, and to question 3 when you ask for uniqueness in law. Okay. The thing is that there is a very nice argument that allows you to extend this convergence to convergence probability. Okay, so this is what I do like very much. This argument it is based on a paper by Shamoff. So this is just an elementary lemma taken in Shamoff's paper, Alexander Shamoff. Okay, this is a very elementary lemma, you will see, but very smart to apply it in this case. Okay, so now I'm going to talk about convergence in probability. And the theorem is the following. So we are in the case of the GFF. Okay, let X epsilon be so you take a modifying sequence with say compact support or circle average if you want. Okay, as you have seen circle average in JSON lecture notes. So you can take it. Well, let's put a bar on this circle average approximation, and if gamma square is less than 2G, the random measure converge in probability towards a limiting measure. So
just a naive question. So, is it true that for a small gamma, it's possible to obtain this thing just from the series decomposition?
sorry?
Is it true that for a very small gamma, it's possible to obtain this theorem from a series decomposition, or from Kahn decomposition, or just by hands?
So just I want to correct. We are in dimension 2, so it's
Okay.
But you say that is it related to a question, or you want to?
Is it true that if gamma is very small, then you can obtain this result just by hands from Kahn?
Well, not necessarily from Kahn, but if you are below the L2 threshold, okay, so gamma square is less than square root of 2. You just take, you see that it converges in L2.
Oh, okay.
You just take the L2 moments, and you see that it converges in L2. So as soon as you have L2 moments, the computations are very simple. So we are going to do the proof now of this theorem. And the first, I'm just a bit annoyed because I need a variant of this theorem here to show this theorem. But the proof is the same. But my statement, let me just claim a variant of this theorem, of a variant of law. You can replace, assume that in the theorem up there, assume that your cutoff approximation x epsilon and x bar epsilon are measurable, say, with respect to a white noise. Call it W, and that W m epsilon, the couple W m epsilon, converges in law towards, so a couple W, say, tilde M, where M is a measurable function of W tilde. Okay, so M is equal to something of W. Then the couple X bar epsilon together with W will converge in law. Toward the same limit in law. Well, actually, so this statement is very natural if you just want to look at uniqueness in general, but it's often very convenient to work with white noise because this is an easy way to construct cutoff approximation, and you have the same kind of uniqueness result for the law. Okay. So now, what you know about the GFF is that if you take X epsilon to be a Kahn approximation, okay, you know that the random measure M epsilon. So first, it is a measurable function of the white noise by construction. Is that clear? And we know that M epsilon converges almost surely. Okay. You see that if I don't know if you remember, maybe the point is the following: is that when you take now we take X epsilon equal white noise cutoff approximation of the GFF. Okay, recall that it was as I remember, I told you that it should look like something like this. Well, this is S over 2. Okay, so here you have a cutoff, which is a measurable function of a white noise. Okay. So your random measure M epsilon is equal to so it is measurable with respect to the value. Okay. So and we know by Kahn that M epsilon converge almost surely toward M, a limiting measure M. Okay. So if you take an almost sure limit of a measurable function, you get in the end something measurable with respect to X. Okay. To W, sorry. Okay. So by almost sure limit, this is measurable with respect to W. So and as I told you, this is a K-Gaussian approximation. So now, as we have by Kahn a cutoff, which is a K-Gaussian approximation, and which converges almost surely, we know that with this variant, or this one if you want. But we know that for every cutoff that are measurable with respect to the white noise, the couple W x bar epsilon will converge towards something, and this something has the same law as the original GMC measure of Can. Is my statement clear? Or? Okay, so now what you know is that you have a first statement. This is that for every K Gaussian approximation x bar epsilon measurable with respect to W, okay, the couple W x bar epsilon converges in law towards the same limit as we got here, okay, towards Wm. Okay, now I want to show that we have the same statement for convergence in probability. Okay. So let me now state the crucial elementary lemma. Well, let's well, we assume that we have a couple which converges in law towards some couple, where MTL is a measurable function of W. Okay, so we have M tilde is equal to f of W for some measurable function of for some measurable function f. Well, then M bar epsilon, the random measure M bar epsilon converges in probability. Okay, this well, this looks like a magic trick, but you will see the proof is rather elementary. Okay, so let's look at the triple. Okay, so now I want to look at the triple here. Okay, I'm not sure, but for the time being, I'm not sure that it converges in law, but at least I know that it is tight. Okay, because I just these components are tight and this one is fixed, so it is tight. Okay, so I can extract up to subsequence, I can extract in low towards some triple. Let's call it W prime, M bar prime, and M prime prime. Okay. So what we know is that if we just we have this triple which up to subsequence to converge in low towards some triple. Okay. If we just extract the two first components, we know that they converges in low towards this couple here. Okay. So if you just extract, if you recall that this couple converges towards a couple W f of W in low. Okay, this means that W prime M prime are equal in low to W f of W. Okay. Okay. And it's not hard to see that this implies that M prime is equal of f of W prime. Okay. Because take the. Is it clear this statement? Okay. Okay. So this is very. This is very elementary because here you have defined on the same probability space. Otherwise, you may have problems on this claim. But this is just why we work on the same probability space for these couples of random variables here. So now I look at the first and third component of my limiting couple. So W prime, M prime prime. Okay. So obviously, this is equal in low because for each epsilon, the third and the first component are fixed. So this obviously is equal in low to W f of W. Okay. So once again, we have M prime prime is equal to f of W prime. Okay, but now these three guys here are defined on the same probability space. Okay, so this means that almost surely M prime is equal to M prime prime. Okay. Okay, so our claim is just that the limiting triple M prime prime is just equal to W f of W and f of W. Okay. So now, if you look at the difference, as we have the convergence in law of the triple up there, first line of the proof, we know that M bar epsilon minus f of W converges in low towards 0. Okay, because as we have the joint convergence in low, we know that the difference here converges in low towards f of W minus f of W, and it is 0. Okay. But if you have convergence in low towards 0, you have a convergence in probability. Okay, we have convergence in probability towards the same measure. Any questions? So it's like, well, I don't know what's your feeling on this, but it's kind of elementary lemma, but it seems like a magic trick. Okay, you just have a convergence in law and you get a convergence in probability. Okay, this is because you have some joint law. The because you have a uniqueness in joint law. Okay, so this is the thing you use here to say that if you have a convergence in law, every limit is a measurable function of your white noise. Okay, this is the difficulty is hidden in this variant here, and if you see this very clever lemma, you just get convergence in probability. Okay? As soon as you know that there is uniqueness in law. Okay. So actually you see that this, just one last comment. Here you may say, well, okay, the question does not exactly fit to the framework I've drawn here, because here my cutoff approximation, I mean x bar epsilon, okay, just one comment to make sure you understand what I mean. Well, you may have doubts about the fact that I proved something in probability, because the question is, I have a GFF, I take a convolution, and the question was show convergence in probability of this random measure, say. And what I did is the following. I took a white noise, I constructed a GFF x bar with this white noise, which is measurable with respect to W, okay? And I took x bar epsilon equal to x bar star rho epsilon, and then I showed you that this measure converge in probability. Okay. So you may say that, well, you just have something which has the same law as the initial object, okay, and you show that it converges in probability, okay. But recall that the convergence in probability does not rely on the way you construct your GFF, because when you look at if you look at this quantity here, for instance, okay, this is exactly the same quantity in this context here or in this context here, because x epsilon and x bar epsilon have the same law. Okay, so this object, you put a bar or not, have the same probability. Okay, this event. So if you just have to prove that this object converges in probability to show that this one converges in probability. Okay, so you don't care the way you construct your GFF. You can take this one constructed with a white noise. If you show that the convolution of this white noise converges in probability, it's okay. Okay. So Well, this is just an illustration of all the statements that you may have about convergence in probability, in law, and the uniqueness of all these measures. And this is an illustration with the GFF, but you can apply all of this with any kernels, provided that you deal with the K-Gaussian approximation. Okay. So now I just want to. This will almost conclude my lecture on this measure. I just owe you a proof about the support of this measure, and then tomorrow I will discuss the connection with random planar maps. So the last thing I want to tell you. Before I go to the support, maybe one open question, which is very interesting, I guess. Well, I told you that for gamma square bigger than 2D, okay, the martingale you get with Kahn theory vanish. Okay, so if you take nice cutoff, say à la Kahn, this measure will converge to 0. Okay. So at criticality, when gamma square is equal to 2G, so if you go to 0, it's not a very bad situation. Okay, the situation is not completely bad if you can find a factor here. Okay, another factor, so that if you take the limit here, you will get something non-trivial. Okay, so going to 0 is not so bad, and it turns out that the way of constructing a non-trivial limit is to do the following thing. Instead of looking at this random measure here, you just differentiate with respect to gamma, and you put a minus, and you will get something like this. Okay. If you forget this term, you take the derivative with respect to gamma of this martingale. Okay. Derivative of a family of martingale with respect to parameter is again a martingale, and you'll get this martingale here. Okay. There is an extra term here. Okay. And actually, this converges as epsilon goes to 0 towards some limiting measure. It is often called M prime, or the derivative martingale, because you have differentiate with respect to gamma. Okay, but this is not exactly the same structure as the measure we deal with in my lecture, because there is this extra term here which is not in the exponential. Okay, and the Kahn comparison principle doesn't work in this framework. Okay, and the very important question is to know whether you can state a lemma of uniqueness in law, say, for this measure M prime constructed like this. Okay, you have an almost sure convergence here, but we don't know if all the measures you get this way have the same law in the limit. Okay, take two different cutoff, x epsilon and x epsilon prime, say. Okay, you get two derivative martingale, and we don't know a general criterion to make sure that the limiting measure have the same law. Okay, and for instance, if you manage to do so, you can identify the limiting measure in the well, you know, maybe about the extrema of the Gaussian free field by Thomas Madol, who is here, and Ofer Zaytouni, Bramson, Jing. Okay, they have a limiting measure in the end. It should be this derivative martingale, but they have a bad cutoff. Okay, so the question is, does their limiting measure with their bad cutoff is the same as this measure à la Kahn? Okay, or variant of Kahn construction. Okay, variant because we are at criticality. Okay, so if you have a general statement, you can identify, for instance, this limiting measure appearing in the study of the extrema of the Gaussian free field. So this is an open question, and in my view, it's a very important question. So now, just last lemma of the support. Suppose that we have X that you can formally write as a sum of smooth kernels yk. Okay, this has covariance kernel k. Okay. You assume that you have a Gaussian distribution, call it X, that you can split as a sum of nice independent Gaussian processes, call them yk, and each of them has covariance kernel k, small k, and this one has covariance kernel big K. We assume that, well, big K is of log type. Okay, as usual. And we assume that the random measure Mn xn square, where xn is the sum of the first n component. So we have a decomposition on a can. Yk. Okay. Well, we assume that this martingale is uniformly integrable. I mean, each time you take a compact set, the sequence Mn of A is uniformly integrable. Okay, the question is, what is the topologic support of the limiting measure? Okay. So this is just a nice 0-1 law argument. So theorem, the topological support is the wall of RG. Okay, and actually, if you just replace the Lebesgue measure here by a general radon measure, okay, you will get that almost surely the topological support of the limiting measure is the support of sigma your radon measure. Okay, so so the claim is that the topological support are the same, but the limiting measure that you get here is singular with respect to the radon measure that you put here. Okay. Well, these are two statements of different nature. Okay. Okay. So how do you do this? Well, let's call. Well, first observe that if you take a set, say a ball, m of b is equal to the integral let's call this measure with n as a superscript, and I'm going to define mn. Mn is equal, the measure mn dx is equal to the limit as capital N goes to infinity of exponential Okay, I can define a measure mn where actually you just put aside the first n terms of your wall expansion here. Okay, and this measure, so this is a KO because xn x capital N minus xn is just the same sum as here, except that you start as capital as small n. Okay, so this is a KO à la Khan. And actually, the covariance of this measure are less than the distribution that you've got here, because you suppress the first n terms. Okay. So if this measure is the limit of uniformly integrable martingale, this one too. Okay, because the covariance here are less than those here. Okay, so you can use Khan comparison principle. B, this is a ball, B ball. Okay. So what we can deduce is that if you take a ball from this inequality, we can say that m of b is less than the integral of over the ball. Here, I just bound this quantity here, which is continuous, by its supremum. Okay, so I can say that this is less than the supremum for x in the ball, gamma xn minus gamma square okay, times mn of b. Okay, and here I can do the same lower bound with an infimum. Okay, so it works provided that that you are sure that almost surely these processes have a supremum over a ball and an infimum over a ball. Okay, so if you assume that your processes yk are continuous here, this is clear. Okay, so here times mn of b. Okay, so now you see that the measure of the ball is positive if and only if the measure of the ball through mn is positive. Okay, so the event m of b positive is equal to the event mn of b positive. So why do I use this relation? Because you see now that the event m of b positive is actually in fact belongs to this following how do you call that? The asymptotic sigma algebra generated by the xn, the yn. Okay, so this is the sigma infini algebra generated by the yk. Okay, and as these fields are independent, okay, you've got a 0-1 law for this event. Okay, so the probability that m of b is positive is equal to 0 or 1. Okay, so now we just have to compute, for instance, the expectation to decide whether it is 0 or 1. Okay, but as this measure is the limit of a uniformly integrable martingale, we know that the expectation is actually the Lebesgue measure of B, and if we take an empty ball, it is positive. So this event has probability 1. Okay. So actually 1. Because we are almost done, because now you can do the same argument for every for a countable let's take Bn sequence of ball generating the open set of Rg. Okay, so as this sequence is countable, you know that almost surely we have m of b n positive for all n. Okay, so if the mass of every ball is positive, okay, this means that the topological support is Rg. Okay, so this concludes my my presentation of this measure, and tomorrow I'll discuss more their applications. If you have any questions. Okay, thank you for your attention.